In the last video, I talked about how we can make a transformer by simply winding a secondary coil over a primary coil with nothing but air inside. In this video, I'm going to finish up this topic by talking about why a transformer is often made using an iron core, meaning that there is usually a piece of iron inside the coils. Now, if we look at the calculations that I did in the last video, you will see that the voltages both in the primary and the secondary coils are directly related to the magnetic field through the magnetic flux. So in this case, for example, in order that we can induce in order that we can support this input voltage of a certain value and therefore an output voltage of a certain value. In order that we can support this input voltage of say 1 volt, now it is necessary, for example, that the magnetic field in the coil be 0.001 Tesla. Right? It is necessary that this magnetic field has a particular value. Okay, and in order to produce this particular magnetic field, this particular magnetic flux density, in turn we require a particular value of the current. So in this example, we have a 0.1 ampere of current going into the primary coil that produces this 0.001 Tesla of magnetic field. And let's think about what happens if we have an iron core instead. If we have an iron core, that will typically increase the magnetic flux density by a few thousand times. Okay, so let's look at what happens if we have an iron core. Okay, I shall start by drawing, say, an iron core down here. So this is iron. Okay, and suppose that I wind the same coil or coil of the same size around this iron core. So this will be a coil, the same number of turns, meaning 1000 turns over same length and with the same cross-sectional area of 10 centimeters squared. And we want to put a 1 volt through it like before. Now, if I put a 0.1 ampere current goes through here, okay, as I mentioned just now, having a piece of iron would multiply the magnetic flux density by by up to a few thousand times. So let me just say that the iron, increases the magnetic flux density by about 1,000 times, just to get an idea, get some understanding on what effect this would have on this transformer. So if this input voltage, this primary voltage, pushes a current of 0.1 ampere into this primary coil, then instead of the 0.001 Tesla the current would give when we have just air in the coil, if we have iron in the coil instead, the 0.001 Tesla would be multiplied by about 1,000 times, so that this time we will get a 1 Tesla, a huge 1 Tesla magnetic flux density. And that's huge. Now, recall that we needed the magnetic field to be 0.001 Tesla, so that if it reaches this value after this time interval of 0.001 second, we would get the point. We would then be able to relate the induced EMF to the 1 volt primary voltage that goes in. So it is, if this input voltage is 1 volt, therefore the magnetic flux density produced here has to be 0.001 Tesla. Okay, so the important point here is that in both cases, we are talking about we're talking about how during this time interval 0.001 second, we want the magnetic flux density to reach this value. So therefore, during this time interval, we don't want a 1 Tesla flux density. We don't want such a huge flux density here. We want a 0.001 Tesla flux density. And what this means is that instead of a 0.1 ampere current, alright, we will need a current that is 1,000 times smaller, so it will be 0.0001 ampere. Okay, so in order to support this 1 volt input voltage, when the core of the coil, the center of the coil is just air, we needed this field. Now what I'm saying is that even if the center of the coil is made of iron, we will still need the same field in order to support that 1 volt input. Okay, the 1 volt input is directly related to the rate of change of flux according to Faraday's law. So the magnetic field flux density should increase to the same value in this same time. So in order that it increases to the same value in that time interval, therefore, I must make the current 1,000 times smaller, simply because the same current would give me a field that is 1,000 times bigger. So therefore, what this means is that I can achieve the same EMF in the coil. Right, the same EMF can be induced in the coil by using a current that is 1,000 times smaller than if it is just air inside the coil. And that is the point. The point is therefore that if we use iron, which increases the magnetic flux density by 1,000 times, we would only need to use a current, maybe not to use, we would only need a current of 1 over 1000 times. So in other words, the current can be 1 over 1000 times smaller. Let me rephrase this so that it's not misleading. Because the iron can increase the B magnetic flux density by 1000 times, okay, this means that the current would be is 1000 times smaller, right, to give the same magnetic flux density. Okay, because if the current isn't 1000 times smaller, then it would give a magnetic flux density that is 1000 times bigger, which we don't need. Now, and if the current is so much smaller, that is a very good thing, because it would really reduce, because if there is some resistance in the coil, which there is in real life, having a much smaller current would reduce the heating in the coil a lot. Okay, so this really reduces heating in the coils. So this then is the main reason why we want to use iron inside the coils. It really helps to reduce the current, reduce heating, and save energy. Not just save energy, we really want to reduce the heating. Otherwise, if it gets too hot, it can melt or even catch fire. Okay, so that gives us one reason. This is actually one reason why we want to use iron. Now, there is another reason, which has to do with the configuration that we normally see. Now, the arrangement that we normally see of a transformer is that we have a rectangular piece of iron. So a piece of iron that looks like this. Either a rectangular piece or can be a circular piece, although that might be not so common, maybe. Okay, so anyway, if I have a rectangular piece of or square piece of iron, ring or loop, then instead of winding the secondary coil over the primary coil, it is now possible to wind the secondary coil over another part of the iron. Now, why would that be a good thing? Why don't I just use a single piece of iron rod and just wind both coils over it? Now, again, that has something to do with the heating. Okay, because if this transformer normally takes lots of power. Okay, and even though using iron would help to reduce the current we need by over 1000 times, okay, there could still be there would normally still be enough current to cause a lot of heating, and it is therefore much better if we separate the two coils. If you have both coils over the same place like this, and they both start causing heating, then they'll start heating each other up, and it just get hotter and hotter, which is not good. But by using iron, we can actually coil the coils in separate places, in different places, and that would really reduce heating. Now, why is it that we can have the coil in separate places. Now it's because of the nature of iron in conducting magnetic flux around it. Okay, because iron is magnetic, the magnetic flux is able to travel around the iron. So in other words, the magnetic field would not spread out like if the coils have just air inside. If it's just air inside, the magnetic field would look like this. It will just spread out like this, as if it just like if it's a simple electromagnet with one piece of iron rod inside. So the field will just spread out. But if we have a square piece of iron ring like this, then the magnetic flux would actually be conducted around it like a current, as if it's an electric current. So it would just go around this. Okay, with there would probably still be some that would go out, a little bit, but those will be quite small, and most of the flux would just go round and round without getting lost. So this allows us to put the secondary winding in another part of this iron ring, and the same or almost the same amount of flux would be able to go through this secondary coil as if we wind the secondary coil around the first coil directly. So because of this, there's no need to wind them over each other anymore, and that would really reduce heating a lot.